So now, without any further ado, I would like to introduce our speaker today. Brian Miller joined EPC in 2015, where he is the Field Applications Engineer for the Eastern North America. He has over 30 years of experience in power electronics as a design engineer and as a field application engineer. At IBM and Sony Ericsson, he designed small, efficient power supplies and battery chargers for laptops, tablets, and other equipment, and designed a custom analog controller IC for laptop DC and battery charging. Previous to EPC, Brian was a field application engineer for Semtech, where he was involved in designs for AC/DC, DC/DC, LED lighting, and other areas. He has authored patents, articles, and talks, and he received his MSE and BS degrees from Duke University. Brian, thank you so much for joining us today.
Thank you, Renee, and welcome to everybody. Good morning or afternoon or evening, wherever you are. Thanks for attending this talk on gate drivers for GaN FETs. To get things started, little overview on GaN FET gate drivers. The driver is the part that interfaces between the PWM, the controller, to the power FETs, and it's really critical for reliable converter operation. We'll go through things like driving requirements, what's needed for the GaN FETs to make them work best, and also for the controller, some protection features, features that protect both the output and the proper operation, and if various things need to be monitored. Some timing requirements. GaN FETs are so fast that it's good to look at the timing requirements to make sure things work in a way that's expected. And also GaN FET specific requirements, some that don't show up with MOSFETs. Okay, now to get into some more detail. First topic, dead time and reverse conduction. You see on the graph on the left, showing the conduction in the reverse direction, the little, for example, over here, the little diode that's part of each of the FET. It works like a diode, but it's a very fast function. There's no reverse recovery, which is nice, but it does have a voltage drop, and the voltage drop is shown here, about 2 or 2.5 volts. And that's something really to take into account when designing the gate drive circuit. The gate driver must include a bootstrap and overvoltage management. So like over here, you want to make sure that the regulation is 5 volts. And also this node here, which affects the regulation of that 5 volts where it sits, it doesn't go too far below ground. So the driver must include the bootstrap overvoltage management. The driver must work with a negative supply voltage, negative switch node voltage up to 5 volts. So if this node goes right here, the switch node goes down to negative 5 volts, you want the driver to still continue to work in a proper way. Okay, next topic is the speed. GaN FETs switch very fast. And this is applicable to half-bridge drivers. You can see an example over here. This is an upcoming FET being switched at 150 volts at 5 amps. And look at this. This is 73 kilovolts per microsecond. Now, if you have a half bridge that can't take that, or an isolator, or something else in there that's sitting on the switch node, that could create problems. So you want something that can actually take that speed. You want the higher voltage rated FETs to switch faster. I mean, they do switch faster when it comes to this. So this is one example. There'll be others coming. Increasing the gate resistances can reduce the dV/dt. For example, if this is too fast for the system, you can decrease the speed. That's very easy, actually. But the problem is you would increase the losses, and that's kind of against the point. You'd like the best operation, the best efficiency. So it's good to have a gate driver that can take the high speed on the switch node. Another topic is the threshold voltage. GaN FETs have a low threshold voltage of about 0.7 to 1.5 volts. Therefore, you want to ensure a good off state. For optimum performance, it's good to have gate drivers with a separate turn on and turn off outputs. This is the top gate driver. You can see the resistor here on the top, a different one on the bottom. This is not required. Many gate drivers just have one output, GaN gate drivers also. But this is really optimum. So you can control the turn on and the turn off current strength and resistance separately. One thing to avoid is the circuit below. You've probably seen this a lot where a diode is inserted to give a turn off resistance, which is different from the turn on resistance. Now you really don't want to do this because the diode will have a drop. Even a small Schottky will have a drop. And that'll eat into the voltage margin here. If you have 0.7 volts minus about 0.4, you're at 0.3, and a little bit of noise could have a slight conduction. You really want to avoid that. So just a very simple circuit with just resistors. That works the best. That's what's in evaluation boards and almost all successful designs. By the way, on this topic, there's no need for negative voltage drive on EPC's GaN FETs. Having the output driver on the low side go down to 0 volts, that's plenty. That's good for operation. Okay, next topic, GaN FET overvoltage management. So you can see over here that the GaN FET's right here, and you would like a regulator or some kind of management to keep this voltage on the capacitor that feeds the upper gate driver below 6 volts. The maximum stated maximum on the gate is 6 volts on the EPC data sheet. There's actually very good reliability if you run continuously at 6 volts, but you don't get much benefit much above 5 volts. So if you have a gate drive voltage of 5 volts, that's probably about the best. It also allows for a condition where if you have ringing. So for example, if there's some inductance in the gate path coming from the driver through the gate, back through the source and over, and this applies for both a top FET and for a bottom FET, then you can have some ringing. It's best to damp out this ringing with a resistor, ideally with good layout to minimize the source of the problem in the first place. But that's not always practical to completely eliminate it. So we put an equation over here which can be used as guidance for the which includes the gate loop inductance, common source inductance, the inductance would sit right about here, right in the switch, common from the gate loop and the power loop, and the gate capacitance of the gate node. So you put these together and have a resistor, at least the value that's calculated, to dampen out the ringing. Next one's undervoltage management. It's the same basic idea. When you turn off, you would rather not have it go down and up. Now you might think going down, that's no problem. That's true, it is no problem. But it could also ring back up, hit the threshold, kind of like on the bounce back up as it goes down again. And that's something you really want to avoid. So again, the ringing is bad because of the bounce coming back up, not because of the negative point here. So with a similar kind of method, analyzing the same kind of equation, same type of thing, the loop inductance, gate source inductance, capacitance, you can find a resistor for the R off resistor that would help dampen this ringing and especially prevent the ringing coming back up that could go above the gate threshold. Another topic is undervoltage lockout. You don't really want to have a transistor that's not optimally driven. You don't want it to go in the active mode or have the RDS on go too high. So you'd like to monitor both the upper and the lower gate drivers to make sure they're okay. Minimum recommended gate thresholds, 4 volts for enable and about 3.8 for disable. One thing to be careful of is some controllers may have their own thresholds. And I've seen cases where you can adjust the gate drivers for, say, 5 volts, but the undervoltage lockout could be even above 5 volts, or 4.9 or 5.2 or so, worst case. And that's clearly bad. You would be right on the edge of turning off the gate drivers. So something like this gives plenty of margin, yet ensures that the gate voltage is high enough. Like I mentioned, this applies to both the upper and lower FET drivers. And especially for the upper driver, it's very hard to measure this. Measuring this capacitor, which is the gate voltage that goes into the driver, that's difficult because the switch node bounces around at high speed. So even with a oscilloscope probe on the switch node and the top and subtracting those, it's still a challenge. It's a differential signal challenge to measure. So having undervoltage lockout on the top driver just adds another level of protection. Okay, the topic is propagation delay and matching. So the input signals here, the high input, low input, this is measuring from the inputs here to the outputs, being the drivers right here. See a little graphic of the signals going through. The on-off delay should be matched within 5 nanoseconds. Maximum delay should be limited to 50 nanoseconds. So in other words, you don't need the input to the output to react in 5 nanoseconds. That'd be a very quick gate driver, and that's not really necessary. But more what's necessary is the matching between the two paths. You wouldn't want to have too much tolerance or too much delay there, because you like to have low dead time. We have to make sure that with the tolerance of manufacturing of the gate drive and other kind of situations that you have a pretty well controlled matching. So for example, if you set the dead time at 2 nanoseconds and the gate matching is 5 nanoseconds, you could possibly have cross conduction. Maximum gate delay should be limited to 50 nanoseconds. That helps with the loop performance and overall performance, feedback into your controller. So this little graphic illustrates turn on delay from when this input signal comes to the output signal. Okay, next, minimum pulse width. Now this ensures proper turn on and turn off. So with minimum turn on time, well, actually the minimum off time, that's a good one to talk about, because during the minimum off time, that's when the bootstrap turns on and charges up the capacitor for the upper gate driver. If the bottom gate driver never turns on and tries to do 100% duty cycle, this capacitance will just discharge and there'll be no voltage for the upper gate drive and everything will turn off. A more subtle form is if the bottom gate is on for a very, very short time with a very high duty cycle for the top. You need to ensure there's enough time for the capacitor to reliably charge. So minimum off time is important for that type. With frequency, you can adjust the capacitor to make sure there's enough capacitance to hold for the whole on time. But the duty cycle and minimum off time is still required just to keep the capacitor charged up. Again, here's a diagram of the voltage, for example, the 5 volts coming through an internal bootstrap capacitor, a diode going into the bootstrap capacitor, and the path down here. Okay, there are several compatible gate drivers for GaN. It's really nice. In the last few years, there have been quite a few additional GaN compatible gate drivers. To go through some of these, first category, single gate drivers. There's one that's been around for a while from TI that includes a regulator, includes an LDO, so you can feed it, I don't know, 12 volts, 10 volts or something, and it'll have a precision 5 volts gate drive. And it's very fast, and it has 2 outputs. And also there's another one from TI that's very fast, and also it's very small. There's a picture here, but it's so small it's good for very tight places. And there's others here. Not listed are some from Analog Devices, which are isolated. Those are very nice too. A very popular category is the half-bridge gate drivers. You notice there's quite a few here, and this is not even complete. The first two, there's a very common footprint, very popular footprint, shown here, the ball grid array here. 2 of them, one is from UPI, 1966E, another's from TI. So these 2 are both in this footprint. Very well proven and very good performance. There's automotive version of this Texas Instruments one, AEC meaning automotive qualified. There's a 200 volt one and 2 from On Semiconductor, which are very interesting. One that goes all the way up to 650 volts. And you might ask, well, gosh, 650 volts, that's awfully high for EPC GaN, which kind of top out at less than 400 volts. But you can use such, say if you want to use a multi-level converter, or for some reason, put a FET way up above the voltage range. So still, say a 200 volt or so FET, but just lifted quite far above ground. This driver will drive it, that kind of situation. It's also the same thing, 150 volts. And there's 2 interesting ones down here from Silicon Labs. They have a whole series, including a single one that's isolated. So there's an isolator between the input and the output. You can have 2 completely different grounds. They're rated 650 volts, and they're also automotive approved. And as I mentioned, additional gate drivers are in development. Some we really can't mention yet because they're not publicly released. And like I mentioned, this list is not complete. One thing that's interesting that I'll talk about later, but if you look at these 2 on-semi part numbers, both of these have an interesting feature that you can put, go up the page. Some designs have a current sensor resistor right here in series with the source. That's not ideal for the gate loop. It's in several ways, but the on-semi driver or drivers have another connection, so the bottom gate drive can float up to plus or minus, I think it's plus or minus 3 volts. And that can really help to have both a a source connected current sense resistor and good optimum and gate drive. Another topic is adopting MOSFET drivers for GaN FETs. And there's all kinds of situations. There could be specialty ones, whether it's built into a controller, whether it's something that has to be used for one reason or another. And the question comes up quite a bit. Can you use some MOSFET drivers for GaN FETs? Is there a way to just adjust things? And the answer is a solid maybe. In many cases, the answer is yes. So let's go through a few conditions here. First, the driver must use an external bootstrap diode. You can see the picture right here. So here's a half-bridge driver. You see an external bootstrap diode. Bootstrap diode is good because you can put a current limiting resistor in here too, and you can also control what this diode does. You want to ensure the undervoltage lockout and operating voltage match the GaN FET gate. To put it briefly, make sure it can run at 5 volts with an undervoltage lockout that has plenty of margin if there's any kind of noise or a little bit of regulation error in the 5 volts. You want to add measures to prevent bootstrap overcharging. In other words, charging this capacitor too much, which would overvoltage the gate of the GaN FET. So a few things have been done. And there's examples in some controller data sheets that show this, and there's EPC reference designs too, if you would like to go into detail or have questions about that. The first one is to add a 5.2 volt Zener clamp right here. It's not on the gate, because that would load down the gate, but rather on the capacitor that feeds the upper gate driver. And it's a small signal one, isn't it? This isn't it's not a big power one. It's mostly just to take care of any spikes that make its way through. So that keeps the regulation up. And again, you can go up to 6 volts here, but there's no real point. So a 5.2 volt Zener works well. The second one, the series current gate limit resistor right here. During any kind of transient, just limit the current that goes into the capacitor. That'll also limit the current that goes into the Zener clamp. And the third one, you'll see here, there's a Schottky anti-parallel diode. And you could say, well, why is that needed? Because there's a diode right here as part of the GaN FET. But as we discussed earlier, the diode function that's part of the GaN FET, you can think of that as like a 2.5 volt drop. When that conducts, it effectively lowers this side of the capacitor 2.5 volts below ground and could overcharge this capacitor and make the clamp work harder. Plus also, some gate drivers, some controllers can't take this node going down to minus, say, 2.5 or minus 5 volts. So this will help. And typically this can be, say, a 1 amp or 2 amp diode. It only conducts in a very short time, just during the dead time, which is typically small for GaN FETs. So if it could take a high peak current, the Schottky diode, that really helps in multiple ways. And small to limit the capacitance too. Okay, next topic, synchronous bootstrap supply. Now, as we mentioned before, GaN FETs are very fast, and sometimes they're used in very fast power supplies. Some example of those are things like wireless power, where there's a 6.78 megahertz frequency slot that's allowed for this. So because of FCC and other regulatory standards around the world, you really have to use the 6.78 megahertz or multiples of that. A lot of the gate drivers will work there, except one problem. There's an internal bootstrap diode in a lot of them, which induces loss into the upper FET. So because of the processing of the gate driver, it's not a Schottky diode, it's a PN diode. And the PN diode has reverse recovery. We'd like to get rid of that, but we still need the function. So the basic idea is to replace that diode function with a GaN FET. The GaN FET can turn on and off. And you can control when that turns on and off. And again, with the GaN FET, there's a diode shown, but there's no reverse recovery in this diode, unlike the diode that's not being used anymore. It also works as a regulator, bidirectional current flow. So this capacitor here that powers the upper gate driver, you could have current go both into it to charge, or if for some reason something happens and voltage comes through something else and overcharges the capacitor, and go backwards into the 5 volts. So that's kind of nice. And that's also in some audio systems, that's nice, even for a lower frequency, to have this bidirectional current flow to regulate the voltage on the upper gate drive. Again, this works best at high frequencies. There are applications that are sensitive to switch node distortion. For many designs, this isn't really needed, but it's a great function that EPC's applications engineers have developed as an optional for high frequency. So some details on this, how to make this work, the timing. So to go through here, we'll show some waveforms. In red is a switch node. This is the power waveform on the switch node, going down and up. Going down, this is off, and you'd see the bottom FET gate signal turn on for the lower FET. The gate signal this is, so you'd have a slight delay for the FET itself. In green, is a gate signal for the boost. The gate, the tiny little GaN FET we showed before is so small it's going to turn on very fast. So a little bit of delay is good for that one. The timing, turn on delay. You want the turn off to be immediate. Right here would get into the rise time of the gate signal. So you want that to be immediate. Off state margin to prevent it from conducting any of the power current. You want just to charge up the gate driver for the top FET. You want some drain resistance to prevent overvoltage. So let's go through a circuit. To start off with a circuit, you'd want a tiny GaN FET. This one's a 3 ohm GaN FET, 100 volts. The size of this is 0.9 by 0.9 millimeters, extremely small and extremely fast too. I mean, GaN FETs are fast, but this one is extremely fast. And that also explains the need for a delay, because there's almost no delay of turning on this FET. Here's start of a retrofit. I'm going to fill in these blanks, don't worry about that, of how to do the sync boot implementation for high-speed circuits. Here's the power FETs once again. Here's the gate driver. And many of our boards, the EPC boards, you'll see the TI LM5113, which has now been upgraded by TI to the LMG 1205. So that's a typical one we use in some of our boards. And you'll see in gray the internal diode that we're trying to eliminate its function to keep that from being turned on. So to go through some topics, first you add the FET. Here's the FET added in a way that will directly charge up the top gate driver. Second, you want to add a level shifting capacitor and a charge diode. So this is a charge pump. Every time this node goes down, it'll charge up this capacitor. And then as the negative part of this goes up, this whole thing will go up. So for example, 5 volts in here will charge this to 5 volts. But if you put 5 volts on the negative, you get 5 volts plus 5 volts equals 10 volts at this point. So just a simple charge pump. Another key is to reduce the supply voltage going into the gate driver. The reason there is to keep this diode from being forward biased. And some timing resistors. So the turn on delay, some bleeding off of this, and immediate turn off, and a blocking, so you get the get it raised here. And you look at where this whole circuit is connected. It's connected to the bottom gate driver. And one question might be, well, gosh, it looks like that puts extra load on the bottom gate driver. But in reality, this circuit has very small capacitance on the diodes, the large values of resistors, so it almost doesn't affect the gate driver in any meaningful way. A footnote down here from some of the papers and some of the boards and so forth that will describe that usage of this. That's quite a bit, but it's kind of interesting. One more part I forgot to add, drain inductance damping. So as you saw before, this is a resistor going into the capacitor, as in with some of the other ones, to just limit any peak currents going in. Okay, for a little bit of a review, step back just a little bit to where we started. With a power supply, you can have a controller, a PWM controller, whether it's analog or digital, a gate driver, and some power FETs, in this case, a half bridge. Different ways to arrange this block diagram are commonly take the controller and the gate driver and have that one IC, so built together. Can be like this, or it can be higher functions. Higher functions meaning, say, a 4 FET buck boost. Those are popular with GaN FETs. And using some of the techniques in the previous slides, to make the built-in gate drivers work with external GaN FETs on those type of controllers seems to be growing in popularity. So this is one kind of division. A new kind of division is to instead take the gate driver and combine it with the GaN FETs, not just two die in one package, which is done and has been done, and there's examples on sale for that, but also a new one is to put all of this in GaN onto one chip. So let's go to the next slide. An example from EPC, a part here, and this is the block diagram. These are power FETs, not just part of the gate driver, but these are the power FETs. And you can see them here, the big structures. So this is an 80-volt half bridge, the whole thing, with two inputs, logic level inputs, with different protection, a level shifter to drive the upper gate. And you'll see right here, we just discussed sync boot. There's a transistor right there. So this is built in, and it's driven off the lower gate drive, but it's in the logic block here. So that helps to make this a very high speed, high efficiency system, whole power block. A little bit of details on this. Again, the gate drivers and FETs are on one GaN die. You can actually see some of the transistors there. And the way GaN is, it's a lateral device, so that while these are 80-volt FETs, the power FETs, the transistors inside the gate driver can be much lower voltage, maybe 20 volts or so is fine. And they can be optimized in the same die. That's why they don't take up as much space as they would be otherwise. Another nice thing is the gate drivers can be matched to the FETs. They can exactly drive the best requirements for the particular GaN FETs. The sync boot's required. And you can imagine with layout, you know, there is no layout here. It's done for you. It's internally very short distance. You can actually see it over here. You can see the gate driver right here in one of the FETs, and there's the distance of the gate driver. And this is very small. This whole chip is about 10 square millimeters. And again, layout friendly. You can see the near zero common source inductance. Everything right in the chip and so close, that kind of takes care of it there. We're reaching the end. This is the some additional resources. We have links. There's lots of different app notes and papers that have been done. Here's a list of a few of those. Also, field application engineers like myself and others are ready and eager for your emails. And I imagine there's, I see some questions building up here. So that's another topic where we can go further. That ends the presentation part. Thank you very much.
Great, thank you, Brian. So yeah, now we're going to start answering some of the questions that have been submitted during the presentation. As a reminder, you can continue to submit your questions by typing them into the Q&A feature at the bottom of your screen. All right, Brian. So our first question is, I think you may address this, but maybe I don't know if you want to expand on it. Is it possible to connect GaN FETs to standard MOSFET half-bridge gate drivers? And if yes, could we expect a better performance compared to standard MOSFET? And can you recommend the best adaptation interface for it?
Yeah, I covered that in a little bit, but it's a very good question, and it's a popular question because the easy answer is just, well, just use a GaN gate driver, but there's all different kinds of reasons. It gets into details, you know, things like I mentioned before, the speed. Can it take the speed? Can it take the drive voltage and so forth? And we do have some reference designs. To get into more detail, well, if you want to see it on a controller data sheet, it's kind of interesting. There's a part from Linear Tech analog LTC 7800. I think it's a figure in the back. One of the example circuits has EPC GaN FETs in it. and shows the adoption there on that one.
Okay, next question is, in case the FET is turned off with a 0 volt, how can one deal with the crosstalk or Miller turn on?
That's a good question. The Miller ratio of the GaN FETs is such that we've determined that if you have a GaN FET that's off and you have a transient on the drain, no amount of transient on the drain will make the GaN FET turn on. In other words, no transient on the drain can induce a spike on the gate to make it go up above the threshold to make it turn on. So yeah, that's a real nice feature that was added years and years ago on the EPC GaN FETs. That it's one less thing to worry about. So the Miller ratio is under control there.
Okay. So this question is specifically on slide 5. I don't know if you want to go to slide 5.
Okay.
It says, is there any better option rather than using diode with RG off while using single turn on off gate drivers?
Let's see, is there a better option to say again?
Sure. Is there any better option rather than using diode with RG off while using single turn on / off gate drivers?
Yes, just one symbol resistor is good. In a lot of cases, in a lot of EPC boards, you'll see, even though there are separate ones, a lot of times they'll use the same value resistor, say a 1 ohm or 4.7 ohm or something like that anyway. So if you have a GaN gate driver just with one output or another one you're going to use, yes, just one resistor. And make sure that one resistor isn't too high so you do have a good turn off and a turn on. So you lose some flexibility, but yes, it's okay. There's examples of those also.
Okay. All right. Next question is, can we use ferrite beads for R on to limit the ringing effect in the gate loop for GaN switch?
It's probably best not to. We think it's not good. Yeah, I know what you mean. There's a lot of MOSFETs that have that, and there might even be some other GaN suppliers that do have that or think that's okay. But for EPC's GaN FETs, it's not good. The best thing is just to adjust the resistor values, and that'll take care of it. Adding inductance, even from a small bead in the gate drive loop, just really just hasn't worked well in our tests.
All right. The next question is, can you explain why the output driver needs HOH/HOL, LOH/LOL at the same time?
So why it needs these?
Mm-hmm.
Yeah. I think a few reasons. One is for optimization of the drive. If you want to have a slow drive, then this is one way to do it, and off here. Some of the early GaN FETs, you really did want a small resistor. Say over 5 or 6 years ago, if the Miller ratio wasn't as good in shape as it is now, you really wanted to turn it off well and keep it off so there wasn't any bouncing. But I think now that, yeah, it's more optimization, just a matter of how much you want to go into it. Yeah, maybe it's a bit too strong to say it must have that. I think probably the better way is saying must have that for the best optimization.
Okay, another question is, most of the high voltage half bridge based dual gate drivers do not have separate turn on, turn off connections. Does this limit us to use single gate drivers, or is there a better option?
Again, I think that's a variation on the same kind of, let me go down a little bit. Let's see, where is the list of the different, the half bridge gate drivers of these, the top 3 do have separate on, pull up and pull down. The next one, I'm pretty sure when I looked at it, this is a very advanced high-speed gate driver, 200 volts, very, very good part. It just has a single output per FET, one top output, one lower output, and that works very well. It was designed that way. So you're not limited really to look for that. I'm not sure about these. These all might possibly have one output also. So it really just depends. Do you want something for the highest speed and the lower voltages? Or do you want medium high speed or even just medium speed? A single output would be just fine.
Okay. Let's see. Do you have any recommendations when approaching the limits of the gate driver? How can one stress test the gate driver?
How can one stress the gate driver? I think one way to look at that is the ringing on the gate driver. A lot of them specify, well, for example, if you take one here, it says 80 volts. Looking into the absolute max is 80 volts. Also the limit for the switch node plus the gate drive top. So looking at the different nodes would be good to see just how far you really are stressing it. As far as testing it, I would say go down in resistors lower than you want to actually run the FETs faster than you plan to run, to actually increase switching speed, which would help determine the VDDT. And also, that would also increase any ringing that might be there. So yeah, I think just decreasing the resistance to the gate drivers below what you plan to use would be a good stress test.
Okay, GaN thermal conductivity is less compared to silicon carbide MOSFETs. How do we take care of this?
Okay, that's a slightly different topic with the, let's see if I go down here.
We're actually gonna have a webinar on thermal in
that's right. Yeah, that's a good advertisement for our next webinar coming up with thermals. I'm not sure if I'm on the list for that or what. Here's a die here. The GaN FETs are very good for thermals because of there's no package around them. So there's no layers of things that kind of hold in the heat. Heat can get out the bottom on these pads. You can see the pads, there's the junctions right there. There's a very close thermal route. And the backside, which is not shown, it's a silicon wafer of the GaN on top. And that's a great thermal conducting surface also. So even though the GaN is very small, there's a very good conduction path from the junction out the bottom and especially out the top. And there's some EPC app nodes too, which go through different ideas of using thermal interface material, having a small gap. And we've gotten incredible performance, thermal performance out of these, out of the FETs. You only have to see the measurements to actually believe it. When I first saw it, it was kind of hard to believe myself, but then you see actual measurements and you say, yeah, these are small, but these are very, very good thermally.
Common source inductance affects the driver's speed and efficiency. Is there any way to neutralize it other than reducing it?
To reduce it. Well, good layout, obviously, but that's reducing it. As I mentioned before, there's that, if you have a circuit with a sense resistor, using a driver that connects right to the source rather than to the bottom, rather to the ground node, might be a driver that's referenced to here instead of referenced to ground. That would also do it. I think reducing it might be the best. And the layout summit webinar, which was 2 weeks ago, I think that did go into some detail on how to lay out with 2 different grounds, a logic input ground and a power ground. Yeah. Maybe that would help reduce the effect of that.
And that you can get a copy of the recording of that webinar on the EPC website if you missed it. Okay, GaN FET datasheets don't have delay times or rise and fall times defined in them. How do we determine how fast we can switch these devices?
Yeah, that's a very good topic. And that's, I think it's even the topic for some of the ones within EPC. How do we tell how fast our own GaN FETs are? It's almost like a limitation of the gate driver and external factors. You take the little one that was used for the bootstrap, my goodness, just very fast. And we thought there was a certain speed. And then, TI came out with a real good single gate driver, the LMG 1020, that just pushed it further. So it's mostly due to external factors as far as delay time with, say, drive resistor and parts. But yeah, I mean, it sounds like an evasive answer, but it's really not. It depends so much on external things. There's no package on the EPC GaN FETs. You have something like this. Well, there's no inductance of bond wires going from the junction to this that, limit. So you can have very tiny inductance. So perhaps a good way to look into that is to use a simulation like a SPICE or so to see in a particular application what kind of speed you might expect to get. And there's continual work on the models too, the SPICE models. And keep those improved. I think that's probably the best way to do it. If we put something on the data sheet, it would be more of a function of the test board we measured rather than the FET itself.
Okay. Does GaN driver need Miller clamp protection to avoid shoot through?
Does a GaN FET need Miller capacitance to avoid shoot through? No. With the Miller capacitance ratio being as it is, the finding was that if you take a switch node, let me go back over to the schematic here. If you take a transient here, there's no known transient we found that would be within the specs of the data sheet of the FET that can induce a turn on of the gate. So no further protection. I think the questioner might be asking about possibly negative voltage or a diode or different clamps, but no, that isn't used in any design I'm aware of with the EPC GaN FETs.
Okay. Let's see. How effective is it to have active Miller clamp in GaN devices?
Active Miller clamp. I wonder if there might be two ways to answer that. One is maybe they're asking about the active dead time management. A lot of MOSFETs have drivers with a feedback mechanism to look at the diode so that there's no shoot through. That's not really needed because there's no reverse recovery in the GaN FETs and the diode here. But also, I think going back to the question, a Miller clamp, a clamp that comes down to keep that off when it's coming on. You need something. If it's open circuit, it could come on. So you want something. It turned off to 0. But I don't think you need special, sophisticated external clamps on it.
What about additional external anti-parallel diodes?
Yeah, that's a good topic. Let me go back up to some of the GaN drivers. I can move the slides. If you have a gate driver that's here, you have a gate driver that's built for GaN FETs, the switch node will come in here, and it'll be typically, the GaN gate driver will know that you could have a low voltage that comes in, and it can take that. So there's no particular need for a parallel diode. Now, a lot of people say, okay, you don't need it for that, but how about for efficiency? You have 2.5 volts on the built-in diode inside the GaN FET, right? And if you have that 2.5 volts drop, then you're going to increase the losses during the dead time, right? So therefore, a parallel diode would help overall efficiency. But no, in many cases, that's not true for a few reasons. One is that the dead time is so short, it can just be a fixed value, say from 5 to 15 nanoseconds. So yes, 2.5 volts reverse sounds like a lot, and it is, but for only say 5 to 15 nanoseconds per pulse, it isn't that much. Another reason is if you put an external parallel diode, a Schottky diode around this, you can say, okay, that's good. There's no reverse recovery in that diode, but there is capacitance. And the capacitance of any kind of power Schottky is something else that just adds output capacitance to the GaN FET. So with low frequency, it might be okay, but that's something that would take a good analysis. Now we do add small Schottkys in parallel to reduce the voltage when using a MOSFET gate driver, but that's only like a 1 amp diode. The purpose is to reduce the voltage during dead time. It's not really for efficiency. I think one of the EPC apps engineers said the efficiency is about the same either way. So to keep the bootstrap and the negative voltage on the switch node under control is more the goal.
Okay.
I hope that answers that question. Let me know if that doesn't.
Yeah, if not, just right back in.
Yeah, that's right. Yeah.
Is it possible to calculate the rise and fall time with different load capacitances?
Load capacitances. I think I assume they mean on the gate driver. I'm not totally sure about how the question, what it means. I can answer two ways. One is I've noticed a lot of gate drivers specify, especially MOSFET ones, very high capacitance loads. Mm-hmm. And when you put these kind of gate drivers, you drive a GaN FET, you get speeds that far exceed what this data sheet for the MOSFET gate driver says it'll do, because the capacitive load is so much less. I would say you could just, I'm not sure if it's just a simple equation or not, how the gate drivers actually work. That's a good question. I mean, another way is the output capacitance of the GaN FET. Maybe that was the question. I'm not sure which output capacitance for there. Well, probably a system simulation would be good.
Do you have any numbers in terms of minimum dead times that we've been able to achieve in a half bridge at higher current ranges, like around 40 amps?
In that kind of range, typically around 10 to 15 nanoseconds is what we put on our evaluation boards. In the lab environment, you can dial things down so you can have almost no dead time, but that's just one board. And you know, if the temperature changes in the gate driver, or you get a second one, or something happens, that's kind of dangerous. So we like to allow the margin. So part of the dead time calculation goes through the matching, not the propagation delay, but the matching of the propagation delay between the top and the bottom. That has to enter in the equation. So that's one minimum. That sets like a minimum dead time. And then you have to add more just for variation on the FETs. But for 40 amps or so, yeah, I think about 10 to 15 nanoseconds.
Okay. What optimum Miller ratio do you suggest to work well with GaN MOSFET to take care of DV/DT and DI/DT?
Well, the good news is I think we're above, we're on the, I can't remember if it's higher or lower than 1, but we're, it doesn't come up much. The question was again, which Miller ratio do you recommend for that? It's kind of built into the FET. So there are some designs that add capacitance from gate to source to increase the capacitance to lower the minimum, to lower the effect of a transient coming in the drain, so that you would basically change the ratio by adding capacitance. But that typically isn't needed. There's a few cases, for example, in motor drive where you have just a huge amount of GaN FETs in parallel, like over 10, I think over 12, up to 20, driven by one gate driver. And in situations like that, things can maybe get out of control and additional capacitors, gate to source might be needed, but I just don't see external circuit modifications needed for that.
Can GaN FETs be operated at no load in a half bridge configuration? Does this cause damage to the gate driver in any way?
No load on the half bridge. I think what you mean is half bridge, no load, meaning no output inductor. I think that's probably what the question is asking. And that's something you'd have to look at. No load, I've seen cases where that, yeah, you can have some things happen. Yeah, there's been some odd situations. The assumption through a lot of this presentation is kind of like a somewhat standard half bridge, and the switch node goes to an inductor and then goes to something else, probably capacitor or a transformer or something like that here. To have a true open circuit and running at high speed, yeah, there might be some. The engineer I was talking to, I recommend just putting just a resistor from the switch node down to the ground to get some kind of loading to help. And that did seem to help to go through some debugging.
Do you have reference designs with 2152 without SW needed?
Go back to that one.
Oh, I'm sorry, buck boost converter reference design.
Buck boost converter design without
with the 2152 without the SW. Yeah.
I'm not sure I understand without the SW.
You can ask them to clarify if you need.
Yeah.
Okay.
Yeah, I'm sorry, I don't quite understand the question. Maybe you're asking, can you take a buck boost controller? Let's see. Well, it depends if it's a 4-FET buck boost. You could use this. You could use 2 of them. If you have the signals coming in, the logic signals coming in. Maybe you're asking, do you have a reference design that takes the high side from a controller with a gate driver and gets it down to ground referenced? We don't have such a one like that. Or a buck boost. Maybe you're asking about a SEPIC converter. We do have some SEPIC converter reference designs, but not using this part.
Okay, so we have someone who's doing a design with the EPC 2152. So for simplicity to limit size, it uses only actively the lower FET. The upper FET is always off and serves just as a clamp/snubber. When the upper FET is always commanded to be off by the control equals 0 volts, is it then needed to have a bootstrap capacitor at all?
Yes, yeah, you really do. The bootstrap capacitor on this part, that's a very good point too. It's there for, it looks like it's there just to drive the upper gate driver. It's not shown in this diagram. It's an external capacitor right here from the gate driver down to here. So it looks like it doesn't do things, but there is some internal logic. So yes, you do need the capacitor there. And whenever the bottom FET switches off, it will boost up here and it keeps the whole internal circuits running well. I don't have the details, but for example, if there's an under voltage lockout signal that goes through here, that wouldn't be good. Turn off everything because this chip doesn't know what if you're not using the upper FET, it doesn't know if you're about to turn it on, even though it doesn't know if it's permanently tied to ground or what's going on. So yes, you do need a boost capacitor.
So we have 2 very similar questions. So one was, do we have plans for more GaN with built-in drivers, which is like the 2152, right? And then, or do we have plans for more integrated power stages like the 2152, but for higher current ratings?
Well, the answer to both are yes, and it's a good topic. I mean, that is a key part for EPC. We have a IC design group. So this is, yeah, the good news is this is the first of a family of parts with, and we don't have the details yet, but going up in current, yes. I think that was the main part of the question. Higher current, right? Is that the?
Yep.
Yeah, yeah. So that's in the works. The other part of the question is, do we have plans to have power FETs with built-in gate drivers? And for example, maybe one FET with a gate driver, just this combination here. And I think some of you out there probably realized that a few years ago we did have some early examples. Mostly just for lab use that we made public of having that kind of combination. Since that time, the output gate drivers has really improved in function. It used to be it had to be a 5-volt logic input. Now with these kind of parts, you can have 3.3 or 5-volt logic, and it just works a lot better. So yes, I think over time, you'll see more FET and driver combinations coming out of EPC.
All right, so thank you, Brian, and thank you, everyone.